Electrolysis of aqueous solutions, Part 2. Electrolysis of aqueous solutions results in multiple species being present, some oxidized, other reduced. Their fate is by and large determined by three factors. First of all, the value of their standard electrode potential. Secondly, the concentration of the ions that are present. And lastly, the focus of this program, the nature of the electrode that's present. Let's begin by recapping the steps we use to attack these problems. First off, positive species in water migrate towards the negative electrode. There they gain electrons and become reduced. You can see your IB data booklet for the equations needed here. Again, we will select the one with the highest electrode potential. Negative species in water will migrate towards the positive electrode, where they'll lose their electrons and become oxidized. Again, we identify the one with the highest oxidation potential. Let's start by considering the electrolysis of copper sulfate using inert platinum electrodes. At the negative electrode, the positive copper would be attracted and neutral water. Here we identify their equations in the IB data booklet, and we can copy them out as they're written because they both indicate reduction potentials. I identify the one with the highest reduction potential, so I would see copper being formed. Now what's happening at the positive electrode? Again, sulfate could migrate there, and water. Identify the reactions that are present in our IB data booklet. You'll notice that sulfate isn't present here. Now, we do have an equation with sulfate in it, but we have sulfate being reduced, not oxidized. We need sulfate being oxidized, where it's a product and it can be turned back into its reactant, as listed in this table. The reason why sulfate can't be oxidized is it's already at a 6+ charge. It can't lose any more electrons. It only has 6 valence electrons. So that's why you don't see sulfate being oxidized in this table. We do still have water being oxidized, so that's the only reaction that's going to occur at our positive electrode. So by default, that's the reaction there. So those would be the two reactions we would see happening if we were to use platinum electrodes. Let's now replace those platinum electrodes with copper electrodes. So I'll list them here on the diagram. At the negative electrode, we still have our same two reactions as we had before. But there's a third reaction to consider here. What about the copper itself? Well, copper is a metal, and metals aren't likely to gain electrons. They're far more likely to lose them. So we don't have to worry about it in this case. So there's the one with the highest potential. Now consider the positive electrode. Again, our sulfate and our water molecules make their way over there, and again, the sulfate we don't need to consider. But what about the copper? Can the copper lose electrons? Well, certainly it can. That reaction is present in our IB data booklet, and so I'll copy it out and reverse it. Of the two reactions I have there, the negative 0.34 is the higher potential, so that's the reaction I would see happening there. So I would see copper metal forming and copper metal dissolving in this particular cell. So it is sometimes possible that the metal electrode can be involved in the reaction. So that's a quick overview of electrolysis of aqueous solutions. Questions are always welcome. Thanks for watching.